Hello everyone. In this concept talk, we're going to be looking at Cartesian 2D vectors, and the problem is as follows. Okay, so given a force vector F, obtain the component of F along a 2D or two-dimensional Cartesian coordinate system. Okay, so this is the question that we have to answer, and a very brief glimpse into history. Cartesian coordinate system was named after the French mathematician and philosopher René Descartes. All right. So here is the idea. Okay, first of all, I have a Cartesian coordinate frame. The nice thing about a Cartesian system or a Cartesian coordinate frame is the directions are mutually perpendicular to each other. Okay, so in a Cartesian coordinate system, the directions are perpendicular to each other. And we have known previously if the directions are perpendicular to each other, then the components of a force along that direction are the same as its projections. Okay, from previously, if directions are perpendicular to each other, then the components are the same as the projections, which means that in a Cartesian coordinate frame, the components are the same as the projections. Okay, so for a Cartesian system, the components are the same as the projections, and which means that we can use them interchangeably. Sometimes I would say components, sometimes I would say projections, but they are the same thing if I'm talking about a Cartesian system. Okay, so that's the important point here. So for a Cartesian system, okay, the components are the same as the projections. All right. Now, with this premise, let me start off by drawing a typical Cartesian coordinate system in two dimensions. We will usually call them as the x and the y axes. You can call them as alpha and beta, or you can name them whatever you want to name them as. Okay, so here is the, let's say, the y axis, which I've drawn here. Sorry, wanted to get this straight. So here is the y axis, okay, and then here is the x axis. So I'm going to label this as the y-axis, this is the x-axis, and these are perpendicular to each other. Okay, now I'm going to take a force. Okay, so here is the force, and the magnitude of this force is capital F. Okay, so first of all, the force vector itself is vector F. Okay, so the magnitude of the force vector, so given the magnitude of F is F, that's one thing that's given, and also the angle made by this force vector with one of the axes is given to us. So let's call this angle here as the angle theta. Okay, the angle theta made by F from the x-axis. Okay, so these are the things that are given to us. How do I find the components of the projection? And this is once again the same rule as before. I use the parallelogram law. From the head of F, I draw a line parallel to the y-axis. From the head of F, I draw a line parallel to the x-axis. wherever they intersect the respective axes gives me the components. Okay, so I'm going to do just that. From the head of f, I'm going to draw a line that is parallel to the y-axis, and because of the fact that these are a Cartesian coordinate frame, that becomes a 90-degree angle. Then from the head of f, I draw a line parallel to the x-axis, and likewise this becomes a 90-degree angle as well, right? And then from the tail of f all the way to where these intersect, the x and the y-axis is going to give me the component or the projection of f on the x-axis, and likewise starting from here to there is going to be the component or the projection along the y-axis. Okay, so I'm just going to write that out. So here fx and fy, these are the components of f along the x and the y axis, and in this case they are the same as the projection. Okay, they are the same, which means that, according to the vector law of addition, if this length is fy, that's also fy. So I can say that this creature here, as you can see, starting from this point all the way up to that point, that is also going to be fy because it's a rectangle. And likewise, if you want to think of it this way, you can call this creature also as fx. All right, and it is fairly straightforward to see that from the law of addition of vectors. Okay, so from vector law of addition, we have vector f is equal to vector fx plus vector fy. Okay, this is the key statement. Now what I'm going to do is I'm going to introduce two quantities, little I and little j, which are the unit vectors along the x and the y axis. So let me first draw them out. Okay, so here is little I, typically with a hat on it, but I'm going to ignore the hat. I'm just going to call it as little I. Okay, and then here is little j. So this is also written with a hat on top, but I'm just going to write it as j. It's your choice. You can write it as little I with a hat or without a hat, and likewise. So little I and little j, these are the unit vectors. Little I and little j are the unit vectors along the x and the y axis respectively. And this leads us to the question of what is a unit vector. Okay, a unit vector is a vector that has a magnitude of 1 and the prescribed direction. Okay, so in this case this is a vector of magnitude 1 along a prescribed direction, which implies that the magnitude of vector I, so if I write it this way, in this case if I write it this way, this is going to be 1. Okay, and likewise the magnitude of this unit vector is going to be equal to 1. Okay, this is why the name unit comes into play, because it has unity, magnitude of 1, and it's along the prescribed direction. Okay, so this is the picture that I have in mind, and I'm going to copy this picture down and bring it to the bottom page, next page. Okay, so here is the idea. So these are the components of f along the x and the y directions respectively. Now we come to a foundational principle in statics. Okay, a foundational rule or foundational idea. Idea or concept. Okay, this is really important, and something that is a lifesaver, especially when you go to dynamics, mechanics, any kind of field of solid mechanics or fluid mechanics. Okay, so foundational idea is the following: any vector can be written as a product of its magnitude times the unit vector along its direction. And typically the direction is called as the line of action. Okay, so along its direction or along its line of action. Okay, this is also another key word that you might have not seen before. Okay, so line of action, for example, the line of action of vector f is I just take the vector f and then I start extending it, maybe I don't want to use the same color, but if I use like a different color, for example, if I just take the vector f and then extend it up here, this is called the line of action of the vector. Okay, so this is the line of action of vector f. Okay, all right, and so if this is indeed the case, then I can write the vector fx, because any vector can be written as a product of its magnitude times its unit vector. Then vector fx can be written as magnitude of fx times little I. Likewise, fy can be written as magnitude of fy times little j. Right, so this is going to be fx times little I. Likewise, this is going to be fy times little j. So which means that if I come back here and I say, okay, vector f was originally vector fx plus vector fy. Now this can be written as fx in the I direction, fy in the j direction. Okay, this is by making use of this foundational idea. Okay, that is the importance of this idea, and I can take this a step further. You see that if I redraw this triangle here, so if I redraw that triangle using only the magnitudes, okay, using only the magnitudes of f, fx and fy, you can pretty much see that if I know the vector f, and if this is a 90-degree angle, and if this is the angle theta, then this is going to be f times sine theta, and this is going to be f times cosine theta, which means that the magnitude of fx is going to be f cosine theta, and magnitude of fy is f sine theta. Okay, so which means that this tells me that the magnitude of fx, which is fx, is f sine theta. Magnitude of fy, which is fy, is going to be f cosine theta, which means that the vector f can be written as, it was originally fx I and fy j. This can now be written as f times cos theta I, f times sine theta j. But f is a common factor, so which means I can take it out, which means that vector f is f times cos theta I sine theta j. And you see now that this is of the form magnitude times unit vector along the direction of vector f, right? Which means I can essentially say that vector f is f times some u suffix f, which is f times cos theta I sine theta j, where uf is the unit vector along the line of action of the vector f. Right, this is quite nice, isn't it? And you can pretty much see the following. Okay, if this was the initial vector f, then if I draw a unit vector along its line of action, then this is going to be the direction of u suffix f. Okay, and one more thing that I want to talk about, the magnitude of the total vector itself, right? So in the Cartesian frame, Cartesian system, okay, if I look at vector f as fx and fy, then it is quite obvious to see that the magnitude of f, which is capital F, is going to be the square root of the sum of the squares of the magnitudes of fx and fy. And it's very obvious to see that if I look at the magnitude of uf for me was cos theta I sin theta j, right? Which means that if I look at the magnitude of uf, this is going to be square root of cos square theta sin square theta, which is going to be the square root of 1, which is 1, right? Which means that the magnitude of uf is indeed equal to 1. Okay, its magnitude is unity. Alright, so that was the big idea for this particular concept talk, is that I start off with a Cartesian coordinate frame, which is x-axis and y-axis 90 degrees to each other. I take a vector, its projection and components will be the same in the Cartesian frame, right, as you can see here. And then I can write this vector in terms of unit vectors I and j. And the foundational idea is that any vector can be written as a product of its magnitude times the unit vector along its direction. The direction is called the line of action. Okay, so that is the same thing, the same word for it. Okay, and then with that idea, we found out that, okay, given the angle theta, this is going to be the unit vector uf along the direction of the force vector f. All right, thank you very much.